Hey everybody, welcome to another IAEI News Live. Today's discussion topic is incident energy and the NEC, and it all starts now. All right. Well, welcome. It's another Tuesday, and it's another 12 o'clock Tuesday for IAEI News Live, and I'm Thomas Dimitrovich, happy to be here to talk about an interesting topic that I think has a relatively, I don't know, it has a history that started a while ago, but recently was revitalized, and we're going to talk today about incident energy and the National Electrical Code changes and code requirements that try to address this thing we call arc flash. So the first thing we have got to remember is we have to have a discussion on what arc flash is, right? And it's all about the electrical worker. Now, an arc flash event is a rapid release of energy. There's no, and I've looked through many references, there's not a standard that actually defines the term arc flash, but we know it when we see it. What I'm showing here is a slow motion video of an arc flash, and this is in a lab environment. There's nobody there in front of that equipment, but this is an arc flash, a simulated arc flash event that has been created in a laboratory to demonstrate the power. And you'll see the what looks like a vibration in the video, and that's not the camera moving. That oscillation is actually the bulletproof window that I'm standing behind when that event occurs, and that shows you the pressure wave that occurs during an arc flash event. Now, when you have an arc flash event, you've got a very high temperature, upwards of 35,000 degrees Fahrenheit. You have a intense light, as we saw. You have the hot air rapid expansion. I would lump. I mean, you have hot air. You have molten metal that becomes vaporized. You've got a pressure wave, and we saw that with that glass that was vibrating. Obviously, you've got the sound and the light. I mean, that it's a very intense event on many levels, as this image tries to convey. So let's talk a little bit about what an arc flash is. And remember, I told you earlier, there is no real definition for the term arc flash in any of the standards. 70E doesn't include one. Now, if I looked at 70E, and I'm using the 2021 version of 70E, if we go to Article 100, what you'll find for a definition, it talks about the arc flash hazard, but it doesn't tell you what an arc flash is. It tells you about the arc flash hazard, and I'll read that to you, but I'm going to read this one to you too. And this definition that I'm showing up, when there's not a definition of the term arc flash, what do? You make one up. So I made this one up. Arc flash is the light, heat, sound, and gases produced as a result of a rapid release of energy due to an arcing fault sustained by the establishment of a highly conductive plasma. And that last portion is really an important piece of the pie, because what you saw in that video, go back to that video, when there is a release of energy, you'll notice the light, right? We see the light, we see the gases, but when that event occurs, around the immediate area, which expands very quickly, is a highly conductive plasma. The current actually flows through the air. And you say, well, if it doesn't flow just through air, it flows through this plasma cloud that occurs, because that creates that pocket of ionization, that path that creates the path for the current to flow in between those conductors. So when you see two conductors like this that are side by side, the initial event will create a chain reaction, and that chain reaction develops a cloud of ionized air, which includes vaporized metals, portions of metals, plastics, steel, copper, all that great stuff is just in the air, which creates an avenue for current to flow, phase to phase to phase. Now, and that's an important thing to remember. You got to understand what happens. And we'll talk a little bit about that force and where that force comes from. It comes from voltage. It comes from the available fault current that is there. What are the capabilities of the circuit? The proximity of those electrodes and closeness to each other. Whether or not the structure, the container is smaller or larger, that helps funnel energy. It helps contain the gases. So once you get something going, it's going. And the only thing that'll stop it is an overcurrent device that will limit the amount of time that the current will flow. We're going to talk more about that as well during this hour. So the establishment of a highly conductive plasma is a very important part of this discussion. Now, let's take a look at how 70E defines the arc flash hazard. It says a source of possible injury or damage to health associated with the release of energy caused by an electric arc. And there's two informational notes that talk about. Informational note 1 says the likelihood of occurrence of an arc flash incident increases when energized electrical conductors or circuit parts are exposed. So we know that the arc flash event, the likelihood, and we're going to be talking about two key words today: likelihood and severity. And any time, and I'm going to ask you to do me a favor, when we look at the different code requirements, when you think about actions that we take in power distribution systems, when you're working on systems, look at your activity with an eye on likelihood and severity. What is the likelihood that something will happen, and what is the severity that something will happen? Two key words we're going to expand upon in this hour. All right, so there's two informational notes. The second note talks about C130.5 Charlie for examples of tasks and increase the likelihood of an arc flash incident occurring. So, and we're not necessarily going to get into 70E. That could be left for another day. But I wanted to go into this document primarily because we want to understand arc flash. And I think it's important to understand that those two words, likelihood and severity, because you know what those two words are from. And I'm going to read it to you. The definition of risk. Let's go to the definition of risk. Now, this is an important, I don't think I have it in this slide deck, but if I do, forgive me. We're going to repeat it again. If there's anything that you know, if you are an educator, tell them what you're going to tell them again, and then tell them one last time. And then maybe they'll remember half of it. Risk, a combination of the likelihood of occurrence of injury or damage to health and the severity of injury or damage to health that results from a hazard. So remember, risk is a combination of the likelihood of an occurrence and the severity of the occurrence. The two very important key words that are associated with risk. Now, what we're talking about right now is the severity. right? So we're talking about what is the severity of an arc flash event. We know we have light, eyes, heat, skin, sound and gases, taking in gases into your lung. As a result of a rapid release of energy due to an arcing fault, sustained by the establishment of a high conductive plasma. Now, the amount of incident energy is dependent upon two critical factors. And I've got to update this because we've just updated the IEEE 1584, and we know that the amount of incident energy is also dependent upon a few other parameters, which we'll talk about. But the two principal parameters that I want you to think about is current and time. And think about what you have control over and what you don't have control over. Do you have control over the current? And you may say, I sure do. I can add a transformer in and reduce the current. You sure can. I can add conductor length and reduce the current. But does reducing current always result in decreasing energy? And the answer to that question is no. Sometimes reducing current, I would almost argue, quite often, reducing current will produce more incident energy. And we're going to talk about more about that in this hour as well. So current and time. I may not be able to control the current as easily as I can control the time. To reduce severity, not likelihood. Remember, I'm assuming when I'm talking about reducing time, which means I'm reducing the amount of energy I let go, that means the event has occurred. I haven't reduced the likelihood of that event occurring because it occurred. I'm reducing the severity. And that's an important, remember, there's two pieces of risk, all right? Now, the next few videos I want to show demonstrate a couple things, and I'm not going to. What I want you to understand is the first video. Let's cycles of current flow, which means I am not clearing the fault quickly. So I'm going to show you that video. Then the next video will show you less time being permitted to flow. And then the next video will show you even less time permitting the current to flow. So let's take a look at that one. And I would say you've got, on the first one, you have about 6 cycles of current flowing. 6 cycles. What is that? Remember, what is one cycle? 6 times 0.016. So 0.016 seconds is one cycle. This is 0.096. So it's 6 cycles, 0.096, not even 0.1 seconds. 0.096 seconds of incident energy is the first video. Let's do that one first. I want to show you that one more time without me in the picture.
We'll never trip that break for itself.
So what you just saw in this video is 6 cycles of current. The temperature. We'll go over the statistics, but I want to point out a couple things. You'll notice that the trough on that upper piece is no longer there. Where did it go? Went right into his helmet. You saw the room fill with air. You saw the pressure wave. You heard the sound. You know that was very loud. The heat, the physical force, the light, and the gases. All of that was occurring. Now, what you'll also notice is there's another person right here who was also in that room. And that person didn't feel the brunt of the force on the chest, but did experience the gases, the light, the sound. Now, just fix this for a second. My data is not showing, but I can fix that. All right, so let's do this. I am going to give it one of these. There we go. All right, so let's take a look at the data. The temperature at his neck, with anything that has a greater than sign in front of it, means the meter was pegged. We weren't expecting it to go that high. So we pegged at 437 degrees Fahrenheit on the neck. The sound was around 141.5 decibels. The temperature on the chest was 122 degrees Fahrenheit. The temperature on the hands were pegged at 437. The pressure on the chest was over 2,000 pounds per square foot. That is I would call that a considerable amount of incident energy that this mannequin had experienced. So now the next, and that was about, I would say, around 4 calories per centimeter squared. So that gives you another perspective. So you had about 4 calories per centimeter square. The arc flash boundary was around 39 feet. And you had 6 cycles of current flowing, arcing currents flowing. This next video is going to be, it'll be less than a half cycle of current flowing. Now remember, in that first half cycle during a fault, that peak current is 2 things. One, it's offset from the x-axis, so it's inflated, and that's based upon the X to R ratio. And if you don't know what that is, we'll have more videos coming forward on these Tuesdays. You got to subscribe. You're going to be hopefully watching this channel on YouTube for IAEI. You're going to subscribe to this channel right now, and I'll explain to you what the X to R ratio means and how it impacts fault currents. But that first half cycle is what we call a doozy, technical term. It's a doozy. It will create the magnetic forces, and it will create damage in the power distribution system. So this next one is less than a half cycle, which is better than the first, which was 6 cycles. But let's take a look at that.
Very good. We got it. Very good.
I'm going to show this again.
We got it. Very good. We got it. Very good.
Now, you saw some force. You heard the sound. The trough stayed on, which was a good thing. The mannequin, moved a little bit, but not much. This individual, the guy that's like right here, not me, but right here, this other yellow helmet, he didn't see much of it at all. And that's a good thing. Now, the numbers on this one, again, 133 decibels, still loud, relatively loud. 143. Now, we didn't peg. The only thing we pegged was the hands, which obviously are right in next to the arc. 143.6 degrees Fahrenheit at the neck, 504 pounds. We went from over 2,000 pounds to 504 pounds per square foot on the chest area, and we didn't have any measured heat on the chest area. So what do we do? What do we know? We know the arc flash boundary is much smaller now. Because remember, what is an arc flash boundary? We knew the first event was around 4 calories. An arc flash boundary is the distance away from those exposed, that arcing event, that distance that gets you down to 1.6 calories per centimeter squared. Something that is a survivable burn. So I didn't have any temperature data on the chest. My Temperature on the NEC was 143.6, and my hands got the brunt of it. So the arc flash boundary, and in that instance, the arc flash boundary is 8 inches. You had an 8-inch arc flash boundary. You had 0.34 calories per centimeter squared. That was a 0.34 calories per centimeter squared. It's enough to scare you. It's enough to wake you up if you were daydreaming, but it's not enough to kill you. Now, that all depends on where you're located, right? There could be other ramifications. You'll definitely be changing your shorts when you go home. Now, the next event has even a faster clearing time. This is less than a quarter cycle. Now, what is one cycle? 0.0016. A half a cycle is 0.008 seconds. A quarter cycle is 0.004 seconds. So as I reduce the clearing time, same event, same available fault current, same type of equipment, I'm reducing the clearing time only. Hence, I am reducing the severity of the event. Let's take a look at this one. They've got to zoom in for it. All right, we're going to see it again. And they've got to zoom in to actually see the arcing event. Oh man, I paused that just perfectly. The event is it's an event, but it doesn't create enough heat. It doesn't create enough gases. It doesn't create enough plasma. You get some vaporization going on, but not enough to do much damage. Now, if I look at the statistics, I got no temperature change. I got sound was too low to measure. I got no change even on the hands who were right there. That arc flash boundary is probably millimeters, to a point where you're getting into a shock hazard as opposed to an arc flash hazard. The incident energy on that one was less than 0.17. The previous one was 0.34, and this one was 0.17. I don't know if I got those backwards. This was less than 0.17 calories per centimeter squared. The previous one was around 0.34. And the arc flash boundary on this one was 5 inches. So the current limitation, and let's just do that again. Current limitation, a current limiting device limits that fault to such a point that you have reduced the severity of that event. All right, now let's talk about the code. Now we understand what an arc flash event is. We understand to reduce the severity, I need to reduce the clearing time. And I've mentioned this a couple times. Risk is likelihood and severity. So I've got to look at all of these code requirements in those eyes, and we will walk down through here. So these are the direct requirements in the National Electrical Code. And I'm referencing, I got all these books over here. I'm referencing the 2020 version of the National Electrical Code. And you know what's funny is my book is so beat up that there are still people out there on the 14 code that haven't even bought one of these yet. And mine's beat up. Anyway, two important documents you should always have, 70 and 70E. So I've got them both accessed pretty close. 110.16, 240.67, and 240.87, three very important sections in the National Electrical Code that directly relate to incident energy and are of recent introduction. 110.26, 230.71, and 230.62. So these, I would say, are related requirements. Why? We're going to get into that. But spaces about electrical equipment, and I'll just give you the teaser here. When I think about these events, in that video I showed you, you think about, I want to reduce the likelihood, and I may not be able to, even if the previous sections, 240.67 and 240.87, both seek to reduce the severity of the event. These, in my opinion, help reduce the likelihood and somewhat give you the opportunity to facilitate reducing severity. And I guess the other thing I should add in here, and I think I will, any place in the National Electrical Code where you have a disconnect helps reduce the likelihood. And we'll talk more about that as we move forward. Now, how about these sections? Ground fault protection of equipment. Gfpe was first put into the 71 National Electrical Code. Look at this. This is the this isn't the National Electrical Code. This is a preprint of the proposed amendments for the 1971 National Electrical Code. And this is how we used to do business. And in fact, in my lifetime, going to the National Electrical Code, they used to have these big books in the back of the room that had all of the public inputs or the public comments. And back then, what'd they call them? I can't remember what we called them back then. I've been using public inputs and public comments so frequently. But anyway, they used to have, everything was printed, right? And I remember having my binders and all this other good stuff. And look at this one. This is the 1968, 71, and then 1974. Look at that. Ooh, they went to blue. They went to blue. Now, if I look at the 1971 23095 was a new section in the National Electrical Code, and it was, I'm just looking at the add a new section, and then there were supporting comments, and then there's a panel recommendation. Ground fault protection of equipment, 1970. Conventional overcurrent protected devices, properly selected in the light of the system of available short circuit current, provide sound equipment protection in the case of normal overloads and low high impedance faults, such as arcing to ground, are more prevalent than bolted faults. So arcing faults, with this public input proposal, right? Report on proposals we had in the past, report on comments. The proposal here was to add Gfpe, which was added in the 71 code, and it was because of the arcing faults that occur inside of equipment. Now, let me tell you, and we'll get into the details on that one, but on this one. So 23095 went in 1971, and it wasn't until 1990 that they added it in 240 and in 215 for feeders. And then in 2014, we added it for branch circuits. Now, and what I was thinking of is the challenge. So think about a service entrance equipment. Remember, that's what this is focusing on. 239. This is all focusing on service entrance equipment. I'll explain to you the recipe on why this went into the National Electrical Code. And I think historically, it is an important thing to understand. And I love history. I love to understand the whys, the whats, the wheres, the whens, and because it puts us back into perspective. Okay, it helps us understand what the original intents were, etc. So in 1971, there were three, in this era in our electrical history, there were three key things that drove the requirements in the National Electrical Code. One, we were moving from ungrounded systems to grounded systems. Why were we doing that? What were the problems with ungrounded systems? The issue that our industry, that any ungrounded system experiences are transient voltages. That's the biggest problem. It's like having a boat without an anchor. Well, your system is subject to the system performance. When a fault occurs in a power system, you can have very high transient voltages. Different changes in the system can cause high transient voltages. And what were they? What is that how does that exhibit itself in a power system? You'll see motor windings being damaged because of these transient voltages. And you think about an ungrounded system, it's not a residential home. An ungrounded system are industrial facilities with a lot of motors and three-phase motors. And what they were experiencing were failures of motors. Now, someone probably somewhere said, hey, during a fault condition, we can operate pretty doggone good, and it makes the system more reliable. So they started grounding. In fact, I worked my first coordination and short circuit study that I ever did in my career was for a Union Carbide plant in West Virginia. It was a Delta system. There was I called it the spider on the one-line diagram, but it was a zigzag transformer because I didn't know what a zigzag transformer was back in the day. This was my first exposure to it. And all my PE that I worked under, he got a kick out of me because I called it the spider. And I'd say, hey, I went out and looked at the spider today. Because on the one-line diagram, it was big and round and it looked like a large spider. But a zigzag transformer is what they used to ground the system. And that helped with calculating fault currents, helped limit it limited the transient voltages, etc. They also helped limit the available fault currents or the short circuit currents, etc. But in any case, they grounded the system. It was a delta. All the transformers were delta. I think it was 2,300 volts, which is an odd voltage, but it was a delta system, and they grounded it via that zigzag. So they were moving from ungrounded to grounded systems to solve those problems. But here's the problem: in an ungrounded system, what is that first fault? It's a gimme. What do we require in the National Electrical Code? The lights to tell you, hey, there is a ground fault somewhere. You're still operating. You're operating on a grounded system now, but that next fault is a doozy. So your goal as a facility engineer is to clear that fault, find out where it's at, what phase is it on, where is it at in the facility, and get rid of it. Because the next fault, you're living on borrowed time. The likelihood and severity. That second fault, likelihood could be relatively high depending upon the first fault. But we know the severity of that second fault is tremendous because you have a grounded system. These fault currents are going to be high. Now, the second thing was they moved from 208 volts to 480 volt systems. Now, what did that do? Well, 208 volt systems, moving the voltage to a higher voltage. What is voltage? Voltage is pressure. So a higher voltage can give you more arcing currents now, which is not necessarily a bad thing, right? Because it's all about the clearing time. But I'm just saying these lower voltages will give you lower arcing currents. But the third change is what really put everybody over the edge. And they went from a 600 amp services to up to 4,000 amp services. So your service size increased. And what does that mean? If I go to a 4,000 amp service, that means my overcurrent protective devices are huge. The instantaneous pickup, which we're going to talk about, is way over there to the right. My arcing currents may have gone up, but not enough in relationship to the instantaneous. So what was happening? During the past several years, at least 5 major cities have reported major electrical equipment damage, and in 2 instances, fatalities have occurred in which low fault currents have persisted for a sufficient time to cause very extensive damage. The 1971 substantiation for Gfpe, arc flash events. These events took lives in various cities, and they noticed the trend. There are numerous IEEE papers, which we'll talk about, that documented the issues. And there was a lot of testing done in the 60s and 70s. And at that time, the technology that was just coming out, literally, was ground fault protection of equipment. And there was one manufacturer in the IEEE documents that recognized that said, look, we understand these. I think it was, I'll throw some names here. Duncan Jacobs is one of those names. There's a few others that have done studies, and there were commentary in the IEEE, Institute of Electrical Electronic Engineers, dialogue that talked about this issue, and that there's new technology, it says, on the market, and that was ground fault protection of equipment. And this went into the code in 1971 to solve what we know today as arc flash events. Now, another low-hanging fruit is Article 225, number of supplies. Multiple supplies to a structure enables smaller overcurrent devices, increasing the likelihood of lower incident energy. So this was a strategic change, I believe was the 2020 code, that let us put multiple feeders or branch circuits to a structure. And that was to solve the problem of, remember the electric vehicle car chargers, where I had to bring 2 feeder circuits to an electric vehicle charger, which violated the National Electrical Code because they said you're only allowed to have 1. And I would have to bring 2 because I'm serving 2 vehicles, okay, or possibly more. And then it also was that issue was exacerbated when we made changes in Article 555 for marinas, where we put ground fault protection of equipment at the service entrance, upwards of 100 milliamps, to go out for feeder protection going onto a dock. And that's because of all the electric shock drowning issues that we're seeing in marinas. Well, that required possibly a change in the design, which would mean you need to pull possibly 2 or more feeders out to a dock. And what is a dock? It's a structure. So it would violate earlier versions of the National Electrical Code, but the 2020 said, no, we're not going to call that. We're going to give you additional numbers of supplies. We tried to remedy the situation in the 17 cycle, changing definitions and all this other good stuff, but 225.30, I think, was what facilitated a solution for those applications. If you're not familiar with it, take a look at it. I think it's a strategically important section. Now, I want to highlight again risk. Definition: a combination of the likelihood of occurrence of injury or damage to health and the severity of injury or damage to health that results from a hazard. Now you got what? You have arc flash is a hazard, shock is a hazard, arc blast is a hazard, thermal burns is a hazard. I think you've got like 4 hazards in 70E. You got arc flash, arc blast, shock. So yeah, arc flash, arc blast, shock, and thermal burns. So 4 electrical hazards. And we want to reduce the likelihood and severity. So let's take a look at each of these sections through the eyes of likelihood and severity. 110.16. Now I'm working out of the 2020 version of the National Electrical Code. I do have earlier versions of the National Electrical Code, but I am going to be primarily looking at 110.16 as an arc flash hazard warning. Now, this section, when it first went into the code, was looking for a label like this on all equipment. It wanted an actual arc flash, calories per centimeter squared, working distance, all this other good stuff. It wanted those types of labels. But what we ended up with when it first went in the code was just a generic label like this that says, here's what the arc flash hazard is, which is just it'll cause severe injury or death, turn off all power before opening, blah, 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 all that good stuff. It's just hey, this is dangerous. And it went from you had to field label it to it could be shipped from the factory. In many of these cases, we put these labels on before it leaves the factory anyway. So 110.16 has developed and changed over time. And now it requires a little bit of both. So if you look at 110.16, you have an A, general requirements, which basically tells you where, some of the general information about how to apply that section. And B talks about service equipment. So at service equipment, you're going to be putting this label and that other label, possibly, or you're going to be putting the nominal system voltage, available fault current at the service overcurrent protective device, the clearing time of the service overcurrent protective device, and the date the label was applied. The exception is if you use a 70E label like the first one I showed you. Now, both of these labels that are in the 2020 code align with NFPA 70E. Okay, one, the parent text tries to speak to the table method, which is in 130.7 Charlie 15A. And I think there's a B as well for DC systems, but you have an A and a B to help you determine PPE. But I'll tell you, there are a few changes that and I want you to be mindful of this. Let's think about a panel board with 6 disconnects. If I have a panel board with 6 disconnects, does this mean I need to put 6 of these types of labels? Now, I'll just point one thing out, just for all of you 70E guys out there, you'll notice this is an old label. It has hazard risk category. We don't do hazard risk categories anymore in 70E. So that's an old label. Probably a bad choice on my part, but it was the only one it was the easiest one I had to find. But in any case, if I have 6 disconnects, when I look in 110.16, do I have to label 110.16, 6 fault currents, 6 different clearing times, on and on and on. And in the back of everybody's mind, as they are applying NFPA 70, the National Electrical Code, and 110.16, they're saying, why am I putting 6 clearing times? Questions are going around in people's heads. But what a label does, it helps reduce the likelihood. It doesn't reduce severity. It doesn't do a doggone thing for severity. All it does is raises your awareness. Now, you could argue that, Tom, if I dress appropriately, it can reduce the severity to me when I'm wearing my PPE. But I'll say it's like wearing a harness when you fall. If you're at a high location and you put a harness on just in case you fall, what is that harness? It is the last resort. Everything else went wrong. Does the harness prevent death? No. Does it prevent injury? No. Riding on a motorcycle, wearing a helmet and all this, does it prevent death? No. No. Could it reduce the severity? Sure. But it's your last resort. You don't plan for that. Arc flash hazard warnings, in my opinion, reduce the likelihood, help reduce likelihood. They don't address severity. 2 other sections, 240.67 and 240.87. 240.87, now this is trying to address severity. Why? Because we're looking at reducing incident energy. This is outside of ground fault protection of equipment, which also sought the same goal, but I would argue is not doing as good of a job, because with a 1 second clearing time, your energy can be very high. And with the fact that a ground fault in those systems will go to a 3-phase fault within 2 cycles, I don't know that Gfpe delivered on what it was wanted to do. But remember, it was the only technology in 1971. Now, in 24087 began its journey in 2011. 2011 National Electrical Code only impacted circuit breakers without an instantaneous. And what was that targeting? That was targeting the big power circuit breakers that had a 30 cycle delay that had no instantaneous. And I call those the double wides. Those are big ones. Those are big breakers. Now, what will happen is you'll see those in selectively coordinated systems. You'll see those in systems, industrial power systems that care a lot about reliability, that want that intentional delay up there at the service equipment so that all the little puppies downstream do their job and clear faults and isolate the faults in the power system to limit the outage to the power distribution system. But what that brings to the table is energy. Because why? Time. Remember what I told you, current and time. It brings time to the table. So 2011 sought just for the double wides, those breakers without an instantaneous, which are only power circuit breakers, because every molded case circuit breaker has an instantaneous. Every insulated case circuit breaker is a molded case circuit breaker, and it will have an instantaneous. The instantaneous is there to protect itself, nothing else. But we leverage that to reduce incident energy sometimes. So I can still get a lot of energy on a molded case circuit breaker and an insulated case circuit breaker and a power circuit breaker that has an instantaneous. So 2014 made a change, 2017, and here we are in the 2020. This section, 24087, has seen change since its first introduction. And I think, like a fine wine, it just keeps getting better with time. I don't know if that's true about wine, but I know that's true about the code. Now, 24067 entered in 2017. And what happened in 2017? They said, wait a second. Incident energy is not discriminatory on what overcurrent device it's under. What's protecting it? It's all about current and time. So someone said 24067 fuses have a similar issue. So we had a code requirement put in for 24067 for fusible applications to reduce incident energy when you've got the big fuses that are very similar to circuit breakers. They move that time current characteristic curve way over there to the right, and they add delay because you're dealing with two currents. You're dealing with the bolted fault current, but you're more importantly, in an incident energy application, you're dealing with arcing currents. And arcing currents are calculated based upon IEEE 1584. So if you don't know what IEEE 1584 is, you can look that up. That is the tool engineers use to calculate incident energy. That tool is based upon test data, tests over and over and over and over, done by the IEEE. Dr. Lee was the professor who helped develop the equations that we use today to calculate arcing currents and incident energy. And although it's not defined in the National Electrical Code, the arcing current is a term that's defined in IEEE 1584, and we calculate two values of arcing current for 1584. And we get two different clearing times, and we get two different incident energy values, and we pick the largest incident energy value. Now, 24087 language says where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted is 1200 amps or higher. You have A and B, and technically in the 2023 code, we're going to fix this. It's A, B, and C apply. So A tells us we need to have documentation. B tells us the methods. If we look at 24087, so grab your code book. 24087 gives us options, gives us 7 options. And the 7th option is an approved equivalent means, which opens the door for new technologies. We realize that we can protect equipment and we can protect personnel. This is there to protect personnel from arc flash events. But a lot of the technologies that we use here in B, zone selective interlocking, we've used zone selective interlocking. I started with my company in 1995. And I was technically supporting circuit breakers and relays and programmable logic controllers. And I would get phone calls on zone selective interlocking. Quite frankly, that was the first time I was introduced to zone selective interlocking. And this is 5 years of doing power systems analysis, design, and studies. I worked on industrial power distribution systems, fossil power plants, nuclear power plants. I never got into transmission and distribution. I always wanted to, but I didn't get a chance to do that. But I did a lot of industrial, commercial, fossil, and nuclear, and I never heard of zone selective interlocking. I never had the chance to employ it. If I would have known about that, I probably would have employed that in my designs, but it was not new technology in 1995, is my point. And it was there to protect equipment. And now it's a part of this for arc flash reduction. So zone selective interlocking, differential relaying, that's been around for ages. Energy reduction maintenance switch with local status indicator. An energy reducing active arc flash mitigation system. I would say this is one of the most relatively new applications or examples of technology that reduce equipment damage and help the electrical worker. You have the instantaneous trip, not being permitted to be adjusted in the field, but the instantaneous trip could be leveraged for arc flash reduction, and so could the instantaneous override. And then you have the approved equivalent means. So you have methods to reduce incident energy, and it's all about the clearing time. So if I have a system that can operate in this red region right here, where I clear that instantaneous trip, where I clear the fault as fast as I can, there is no intentional delay when in that area of the trip curve. That is something that is a critical piece of the pie with regard to being able to clear the faults. I want to be able to take that fault current off as fast as possible. You saw why, right? Right in the beginning, I showed you. I had videos, 6 cycles, half cycle, quarter cycle. The faster I can clear, what's a quarter cycle? Let's take a look at this TCC curve. Great discussion here. 0.01 seconds. What is one cycle? 0.016 seconds. And let me do this. I'm going to delete this. Actually, I'm going to move this off to the side. And this clearing time right here, this clearing time, I'm going to let me just put an arrow in here. How do I put an arrow? Arrow through your heart. All right, here we go. Right here. What is that clearing time? That clearing time is 0.0, 0.01, 0.02, 0.03, 0.03, I don't know, we'll call it 0.035, 0.036. We'll call it 0.036, all right? 0.036. So 0.016, 0.036 divided by 0.016. 2.25 cycles. So 2.25 cycles, I can take a fault and reduce that down to 2.25 cycles with this device. If I can get this to clear at 0.01 seconds, 0.016 is one cycle. 0.016, 0.01 seconds is 0.625 cycles. So it's less than less than a cycle, a little bit more than a half cycle. So the faster I can get my overcurrent protected device to operate, the better off I am with reduction of energy. And this next video is an example of what we call that active arc flash mitigation system. And I think you're going to get a kick out of this one, because this is what saves and protects equipment and saves lives from arc flash. That is, in my opinion, a great example of reducing severity. We've taken the same fault, non-protection with protection, and remember that equipment applied per the code. It is operating and functioning as designed. It's providing that delay. But when you have a problem and you start to have an abnormal event and you let the energy out, you can have that type of a problem. Working space. Space is about electrical equipment. That gives us the ability to reduce the likelihood. Why? Because if I give the electrical workers space to do their job. Now, we can talk about establishing an electrically safe work condition and what you should be doing. This gentleman here is working in an electrically safe work condition. Why? Well, it's a brand new facility, but in any case, there's nothing supplying this. But if there was something supplying this equipment, it would be locked and tagged out. They would have gone through all the procedures and established an electrically safe work condition so they can get their work done. But my point in here is you want space in front of equipment. You want, when the electrical worker is going to put themselves in harm's way, you want to provide space in front of the equipment. You want that ability to get out of that room. You want the egress capabilities. You don't want this type of situation where the electrical worker, if the electrical worker doesn't decide to clean up your garbage and decides to try to get this work done in this tight space, there's a lot of issues going on in these types of images. And I don't need, look, this one here, I took this picture in a store. Keep panel door closed, keep clear, 36 inches. Nobody even paid attention to that sign. Hopefully somebody's not going to be climbing on top of this equipment to work in that panel board. Remember the hazards. Arc flash is just one, shock is another. We need working space. We put working space in to reduce the likelihood of tripping, of falling, of getting yourself into a situation that you can't function properly, whether it is to avoid the hazard from occurring or getting out of harm's way. We establish code requirements in this section of the code for working distance for a reason. 230.71, maximum number of disconnects, helps. I think it might help do a couple things. It could help in both of these, likelihood and severity. Because why? Establishing an electrically safe work condition. What are some of the reasons why you can't establish an electrically safe work condition? If you have to turn off a system that impacts a wide area in the plant, they may say, it's fine. You can shut this down if it didn't control this process over here, because if you shut that process down, then I create a hazard for all of these other people. So there may be a lot of different reasons why you can't establish an electrically safe work condition, including, testing. I mean, that's like the number one reason you would do justified energized work if you're testing and doing things like that. But when I can provide an ability to isolate power within my power distribution system without impacting a wide area of, say, tenants or rooms or applications, better off I am. The 6 disconnect rule also changed things such that I will no longer see a panel board with 6 disconnects. Now think about it. Remember I told you, remember the labels. So when people said, hey, if I have 6 disconnects in this panel board, I got to put 6 clearing times. This doesn't make sense. And they said, well, the label doesn't make sense either for the electrical worker, because they're probably going to use it to try to apply the table method in 70E, but they're staring at bare copper conductor that the protection of which is handled by the utility on the line side of their transformer, which is that primary fuse, which is not going to open if I have an arc flash event, because it wasn't designed to provide that protection for me on at this location in the power system. So 6 disconnect rule started to get questioned. And when we had the barrier requirements, the 6 disconnect rule came under fire again. Panel board with 6 disconnects is no longer permitted. And again, 110.16, 240.87, 240.67, and 408.3 is what drove those. And that's when the barrier requirements were in 408. But then we moved those to 230, and we're going to talk about those. So we went from being able to do this with 6 disconnects, that's just 4 of the 6, to requiring that. And then what do? We barrier that main. And then we prohibit these types of installations anymore. And in fact, the 2023 cycle is going to address those these types of applications. Says, hey, look, this is going to have a main, because when I take that centerpiece off, I'm looking at bus. And none of those overcurrent devices are compartmentalized, and compartmentalization is a critical piece to ensure you are providing that complete protection for the electrical worker. These types of installations are no longer going to be permitted. 230.62, enclosed or guarded. These are your barrier requirements. What am I doing when I add a barrier like this on the primary lugs? I'm reducing likelihood. Am I reducing the energy? No. I'm reducing the likelihood of anybody touching these primary conductors, the exposed energized parts, and causing an arc flash event or getting electrocuted. You're not going to cause an event if you can't get to those lugs. 230.95 Gfpe. We talked about this earlier already, first seen in the 71 code, but here's the Tcc curves. This is what it does. This is a 2,000 amp circuit breaker with a 1,000 amp plug. So this is at 1,000 amps. When I add Gfpe now, I'm permitted to take this curve, this red curve, up to 1 second. I'm permitted by the code to take that to a 1 second clearing time based upon 230.95. This is lower on the and the pickup value is lower. So this is trying to address those arcing currents that are going to occur below the instantaneous pickup of that breaker. And remember, this went in 1971. So the incident NEC and the incident energy, I would say look at sections of the code and try to figure out where does it reduce the likelihood and severity. And what I didn't put in here are all of the areas in the National Electrical Code where we require disconnects. What does a local disconnect on a motor help us do? Establish an electrically safe work condition. Any place where you HVAC equipment, you put a disconnect in front of it. What does that help the electrical worker do? Establish an electrically safe work condition. Establishing an electrically safe work condition can avoid arc flash and it can avoid shock. Those are two of major hazards associated with electricity. So we want to facilitate establishing an electrically safe work condition. We want to reduce the likelihood of an event. And we can do that by helping the worker establish an electrically safe work condition. So any place where you see disconnect requirements and lock requirements for lockout, tagout purposes, and you don't have to just do the bare minimum that's in this document. You can put a disconnect if you know that you have a piece of equipment that for someone who's going to be working on that equipment, they're going to need to hunt and peck to find an overcurrent device to open or a switch to open. Put one there. Help them facilitate an electrically safe work condition. Help them reduce the likelihood of an event. Provide barriers wherever you can. Give them more space wherever you can. You want to increase the likelihood of establishing the electrically working condition, safe work condition. Increasing the likelihood, putting disconnects in. Make it easy to do a lockout tagout procedure. Complex lockout tagout procedures can be confusing, especially if the one-line diagram isn't updated. Updating the single-line diagram is not required by the National Electrical Code, but it can increase the likelihood of establishing an electrically safe work condition. Reduce the severity of the event through controlling clearing time. That is what 240.87 and 240.67 aim to do. If we can take these principles by either increasing the or decreasing the likelihood of an event or reducing the severity of an event, when we design the system, let alone when we're applying this or even thinking about code requirements to put for public inputs into the National Electrical Code to help increase the safety. What we know about arc flash and incident energy today is more than what we've ever known. So hopefully this session will help you think about that topic of incident energy and the NEC. And I hope that I covered I covered a lot of material in 1 hour, but look at this book through the eyes of likelihood and severity, and you might walk away with a different perspective, especially if you understand the hazards of shock and arc blast as well. All right. Well, that is a IAEI News Live, another Tuesday's IAEI News Live with a look at the National Electrical Code with arc flash, and I hope you got something out of this, and I'm looking forward to seeing you next Tuesday or at the Eastern section or the Western section meetings of the International Association of Electrical Inspectors, IAEI. All right. Thanks, everybody. Thanks for what you do for electrical industry. Thanks for what you do for electrical safety. Stay safe. Please stay healthy. Until Tuesday next week. See you then.